We can represent organic molecules in a few different ways. The first one is called the molecular formula. So C6 tells me how many carbons I've got. H13 tells me how many hydrogens I've got. And OH. Now you might say, well, why didn't you say H14? Because what we'll come to know is that the OH group is the alcohol group, and so we like to show it slightly separately. So those are just the atoms that are in there. What is known as a condensed structural formula or a semi-structural formula looks something like this. And it goes CH3. In other words, this carbon's got 3 hydrogens on it. This carbon's got 2 hydrogens. This one's got 2. This one's got 2. This one's got 2. This one's got 2 hydrogens and an OH group on. So in other words, it doesn't show all the bonds, but it does kind of show how these atoms are distributed around. This is a full structural formula of the same thing. 6 carbons, you can see that single bonds exist with the hydrogens over there, and then there's an OH group hanging off the end. So that full structural formula, let's just go back to the semi-structural, CH3, CH2. So what's on that carbon? What's on that carbon? What's on that carbon? All the way till the end where we go CH2OH. So that's the way you do your semi-structural. And then this isn't in the curriculum, but it comes up in pictures quite often. It's called a ball and stick or a filled diagram. And that is showing the carbons as little circles with a different color and the hydrogens hanging off them. 3 hydrogens, 2, 2, 2. And then the OH off at the end. So those are different ways of representing organic molecules. Here are some important definitions. A functional group is an atom or group of atoms that form the center of chemical activity in the molecule. Truth be told, CHs really do very little. It's the other parts of organic molecules that react. A hydrocarbon is a compound containing only carbon and hydrogen atoms. A homologous series is a series of similar compounds which have the same functional group. So there's something about them that's very much the same general formula, and I'm going to tell you a little bit more about general formulas in a second. And each member differs from the previous one by a CH2 unit, and you'll see how that works in a second. We're going to look at some homologous series. So the first homologous series of interest is the alkanes. The alkanes have only got single covalent bonds, and we call that a saturated molecule. Like a saturated solution, we can't add anything more to an alkane. Its general formula is CnH2n plus 2. So let's say we go back to that C6 that we were dealing with. Then it's going to be H, 2 times 6 is 12, plus 2 is 14. So that stuff over there is going to be called hexane. It's only got single bonds in it. Single bonds only is saturated. Unsaturated, at least one double or triple bond exists between carbon atoms, and we'll explain that in a sec as well. So, alkenes have got one or more double bonds in them, C double bond C. And their general formula, if we were to do the 6 again, would be C6H12. Call that unsaturated, and alkynes would be C6H10. Alkynes aren't in the curriculum anymore, but it means that there is a triple bond somewhere in that molecule. I'm going to draw out this alkene over here. It's going to be C, C, C. And then somewhere in the molecule, I'm going to put a double bond. I count out, I only need 1 extra hydrogen there, 1 extra hydrogen there, 2 hydrogens, and then, as you can see, how many hydrogens have I got altogether? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that's how it always lands up working. It's a pattern. Another word you need to know the meaning of is isomerism. Examine the 2 structural formulae below, and both have the general formula C6H14, which we just talked about. But this one's got only a carbon chain of 4. This one's got a carbon chain of 5, each with... This one's only got 1 methyl hanging off. This has got 2 methyls hanging off. So in other words, it's the same atoms, but they are differently arranged. These would have different names. We'll go into naming in a second, but this one over here would be butane with 2 methyl groups, and it would be 2,2-dimethyl butane. And then this one over here would be pentane because of the 5-carbon chain and 1 methyl hanging off it. So it's methyl. And which one is it on? The third, 3-methyl pentane. Isomers are compounds, so here's another definition, which have the same molecular formula but a different structural formula. So chain isomers, something like butane and methyl propane will be chain isomers. That means that the chain is differently arranged. So let's go into that with a bit of detail. So it's going to be 1, 2, 3, 4, or 1, 2, 3 carbons and a methyl group hanging off over there. Both of them are 4 carbons, but it's a different arrangement. That's a chain isomer. A positional isomer would be something like 1, 2, 3, 4, and we've got a double bond on the first carbon, or 1, 2, 3, 4, and we have a double bond on the second carbon. So it looks exactly the same, but the actual functional group is in a different position. And functional isomers mean that they look the same, and we'll go into this functional isomer in quite a bit of detail at some later stage. Acids and esters are very common functional isomers. In other words, it's a completely different functional group. But the important thing with isomers is that they have the same molecular formula. In other words, the same atoms are in there, but a different structure. Looking at alkanes in a bit of detail here, we've got CH4, C2H6, C3H8, C4H10, and so we go on. Methane, ethane, propane, butane, pentane, hexane, octane. And you can see, don't worry about these little wedges, they just mean it's coming in and out of the page, but it really is just like the same as a line. What's important to notice with these alkanes is that as the carbon chain gets longer and longer, the melting points and the boiling points will increase. This is because the intermolecular forces, this is very weak intermolecular forces, because it's a very short chain and there are few positions for electrostatic attraction. The intermolecular forces get stronger and stronger until, let's say, we're down at hexane, which is slightly bigger, or at octane. These will be stronger intermolecular forces, even though these are all non-polar molecules. And what do we remember hold non-polar molecules together? It's going to be London forces. But the London forces are weak when the molecule is small and stronger when the molecule is big. Why? Because there are many positions for electrostatic attraction. Over here we have the alkenes, and the same trend is observed as these alkene chains get longer and longer. Notice your general formula here, CnH2n, C3H336, C4H8. Whilst with the alkanes, it was CnH2n plus 2 for alkanes as a general formula for that homologous series. Alkenes is another homologous series. When little bits are hanging off the main chain, so I'm just going to go with methyl butane quickly, or let's go with methyl propane. There's the H, C, H. Sorry, there's a lot of Hing going on here. This is my main chain. It's all linked together. This is a hanger-on. These are called substituents, alkyl substituents, and when it's only got one carbon, we call it a methyl alkyl substituent. And when there's 2 carbons in a chain like that, so for example, if that went C and carried on a little bit, we would then have an ethyl substituent. And we'll get into a bit of detail with naming soon. These are other functional groups that we're going to explore. So alkanes, alkenes, and alkynes are functional groups. And if you keep adding on to the chains of the alkanes, alkenes, and alkynes, you get a homologous series. You then get a haloalkane or alkyl halide, also known as a alkane. And then you've got the alcohol group. And then we're going to also just be aware that there's something called the aldehyde group, the ketone group. These two are officially not in the curriculum, but somehow they tend to pop up and show their faces in different ways that people can get away with. So with the aldehyde, it's at the end of the molecule, whilst with the ketone, the double bond O is somewhere in the middle of the molecule. Carboxylic acid, double bond O and an OH. And an ester has got a double bond O in the middle of the molecule and a single O hanging out in the middle of the molecule with two side chains. So these are all different functional groups, and if you build up chains around these functional groups, you get homologous series.